In this podcast, I'm going to help you and your study group meditate upon some ideas associated with the mathematics of double slit interference. I'm also going to give you a situation which doesn't look like it can be analyzed using double slit techniques, but actually can be. This experiment is important to physics because it showed that light definitely has wave-like properties. In Thomas Young's experiment, he had a light source that was incident on a screen which was opaque except for two very small slits. On a distant screen, he observed alternating bands of bright lines and dark lines. Young's theory was that each of those two slits act as a point source of light, and where the waves arrive in phase on the screen, we see bright spots, and when the waves arrive completely out of phase on the screen, we see dark spots. These results here were striking because the previous model that light is composed of little particles can't explain the interference fringes which result. This is an image from Young's own paper on his experiment. It shows the two slits A and B and wavefronts emanating from those slits like ripples, and you see on the right-hand side points C, D, E, and F, which are locations of constructive and destructive interference. Now I'd like to help us construct the math of this because I think the current textbook does sort of a hand-waving job at it. Here I have the light source at left, the two slits S1 and S2 that are separated by a distance d, and the slits themselves are separated from a distant screen by a length L. Here I've added a few things to the picture. The first is a horizontal line that connects the midpoint between the two slits to the screen at point O. Since point O is equidistant from S1 and S2, light from the two slits will arrive in phase at point O, and we should expect to see a bright spot. This is called the 0th order maximum. As we move laterally on the screen, that is, upwards from point O or downwards from point O, the light from the two sources will not arrive precisely in phase anymore. As you go farther from O, the light will arrive less and less in phase, so that there will reach a point where the light from S1 is shifted by half a wavelength from the light arriving from S2, and at that point we'll have destructive interference and you'll see a dark spot on the screen. As you continue to move farther from O, the light will be more and more in phase until you can imagine a point P where the light from S1 and S2 are completely in phase again. The first time this will occur is when the light from S2 takes exactly one full wavelength longer to get to the screen than the light from S1 does. And so at this point, labeled P, we call that the first order maximum. And you'll see a bright spot there. Here we start to develop some of the mathematics for this. Here I've drawn a line down from slit 1 so that it is perpendicular to the line which connects S2 to P. That line makes a little triangle, and I've drawn an angle theta there, and I've labeled the base of the triangle as equal to D, which is the slit separation, times the sine of theta. The point of this is that the distance from S2 to P minus d sine theta is supposed to be the same as the distance from S1 to P. So in general terms, if d sine theta is some integral number of wavelengths, that is, 1 wavelength, 2 wavelengths, 3 wavelengths, etc., then P will be a place of constructive interference. Now I've drawn a second triangle and a second angle theta. The hypotenuse of this triangle connects the midpoint between the two slits to P. And the opposite side of that angle is labeled X. So for a place of constructive interference, X will be the distance between the midpoint of the central maximum, the 0th order maximum, and the midpoint of the next maximum at P, the so-called first order maximum.
The usual claim made in texts is that this triangle which I've drawn is similar to the first triangle I've drawn, where the base is d sine theta, and they use that similarity to build a mathematical relationship. I've never seen a very decent proof of that, so I've always considered that to be sort of hand-waving from the texts, but I do have a different proof that arrives at the same mathematical relationship, which I can provide. In any event, the analysis usually goes that you have two triangles. The one on the left, the sine of angle theta, is equal to the base, which is the opposite side, d sine theta, over the hypotenuse d. And then the second triangle, you have tan of theta is equal to the opposite side over the adjacent side, or x over L. But for small angles of theta, tan of theta is approximately equal to the sine of theta. And you can verify this for yourself with your calculator. I think that it isn't until you get it to a degree of around 18 or so that the difference between sine of theta and tan of theta exceeds about 5%. But if you say that L is very, very large, especially compared to D, then you can say that tan of theta is about equal to sine of theta, and so you can set up a relationship d sine theta over d is equal to x over L. And then, because you said that for constructive interference to occur, d sine theta has a length equal to some integral number of wavelengths, then you can replace d sine theta with the expression m lambda, where lambda is the wavelength of the light, and m is some whole number, 1, 2, 3, etc., which is called the order number. If you want to talk about destructive interference instead, the relationship would just be parentheses m plus a half n parentheses lambda over d equal to x over L. Here's a problem that might not look like it has anything to do with the preceding derivation and analysis, but actually it does. So here you have two radio antennas separated by a distance of 300 meters, and they simultaneously transmit identical signals at the same wavelength. A radio in a car traveling due north receives the signals. The question is, if the car is at the position of the second maximum, what is the wavelength of the signals? So I'd encourage you to pause the video here and meditate about how to find the wavelength of the radio signals. If it would help your meditation, you may assume the same pose as this little Buddha. So the first thing I decided to do was determine, can I use the small angle approximation or not? So the tan of angle theta would be 400 over 1,000 meters, and the inverse tan of that gives me an angle of 21.8 degrees. I then took the sine of that angle, and I got a value of 0.371. And comparing the sine of angle theta, 0.371, with the tan of angle theta, 0.4, gives me a discrepancy of about 7.2%. I don't know about you, but I'm not very comfortable giving away 7.2% right off the bat for my analysis, so I'm going to first do this without using the small angle approximation, and then show you the difference with using the small angle approximation. This is the analysis without using the small angle approximation, and we get a value of about 55.6. A word about the order number. The peak at the exact middle would be peak 0, and then the next peak up would be number 1, and then the car is actually at peak number 2. This one is analysis with using the small angle approximation. Remember, that's the one where we said that sine of theta was about equal to tan of theta, so that we could equate x over L with m lambda over d. So here we use still order number of 2 and the rest of the given information to find a value of about 60. So the difference between the previous answer 55 and this answer 60, it's quite a big percentage. So I'd be more inclined to go with the former result of 55. Here's a follow-up question for you to consider. Assuming the car keeps traveling north, how much farther must the car travel to encounter the next minimum in its radio reception? And I leave this question for you to meditate upon with your study group. Thanks for watching.